ever look up at the night sky, like truly look and just think, whoa, how'd all this get here?
Oh, me too.
So today we're diving headfirst into the Big Bang, the ultimate origin story.
Buckle up.
We're talking about the creation of the universe, but don't worry, we're going to break it down so even like a 5-year-old could understand it.
At least that's the goal, right? It is a pretty mind-blowing concept when you really start to think about it. This whole universe from nothing thing.
No kidding. In fact, the source material we're using starts with a line that always kind of stops me in my tracks. It just says, imagine nothing.
Yeah, it's powerful. And I think it's the perfect place to start, right? Because before the Big Bang, there wasn't anything. No space, no time, no matter as we know it.
Seriously, try wrapping your head around that for a second, and then boom, everything changes. Or, well, I guess everything asterisk begins asterisk.
It's not even that something changed. It's that something started where there was nothing. And it's not like it was an explosion asterisk in asterisk space. It was the expansion of space itself. Imagine like a tiny dot, way smaller than you can picture, suddenly bursting outward and just growing at an insane speed.
And get this, that expansion is still going on today, right? Like galaxies are still moving apart from each other all the time.
Exactly. It's like the universe is still being shaped by that initial event billions of years later. But okay, let's not get ahead of ourselves. Let's rewind to the very first moments, like a fraction of a second after the Big Bang.
Okay, so we've got this universe, smaller than an atom, suddenly bursting into existence. What's it like in there? Paint me a picture.
Okay, so close your eyes and imagine the most intense heat and density you can possibly fathom. Got it. Now multiply that by like a billion trillion. It was a sea of particles, protons, neutrons, electrons, photons, all crammed together, bouncing around at unimaginable speeds.
So we're talking like seriously hot, right?
Like way hotter than hot. Think about the core of our sun, which is already mind-bogglingly hot, and then multiply that heat by trillions and trillions. It was so hot that atoms couldn't even form yet. The energy was just too intense for them to stick together.
Wow, okay, so we have this crazy hot, dense universe expanding like crazy. It can't stay that hot forever though, right?
You're right, it couldn't. As the universe expands, it also starts to cool down, kind of like if you let steam out of a pot, it spreads out and cools as it goes.
Yeah.
This cooling process was gradual, but it was absolutely crucial for everything that came after.
Okay, I think I'm starting to see where this is going. So the universe cools down and things start to, chill out a bit. Is that what finally allows the first atoms to form?
Exactly. As things cooled down, those particles that were bouncing around so wildly, they finally had a chance to, link up. And the very first atom to form was hydrogen, the most basic and most abundant element in the universe.
So hydrogen, the element that makes up most of the stars, including our sun, it all started with this cooling process.
Yep. And here's where things get even cooler, literally. With the formation of hydrogen, light could finally travel freely through space. Before this, the universe was basically a dense fog. You couldn't see through it because light couldn't get through.
So it was like the universe had its own let there be light moment.
Kind of. This era, when the universe became transparent, it gave us something we call the cosmic microwave background, or CMB. It's basically a faint afterglow of that early universe that we can still detect today. It's like a baby picture of the universe.
Wow, that's incredible. So, okay, we've got atoms, mostly hydrogen, spreading out in a rapidly expanding universe, but we're still a long way from galaxies, stars, planets, all the cool stuff we see today. So how do we go from this massive cloud of hydrogen to, asterisk, everything asterisk?
Well, that's where gravity steps in and really starts to shake things up. Over vast stretches of time, gravity starts pulling those hydrogen atoms together, forming clumps. And as these clumps get denser and denser and they start to contract, they heat up. And that's when things get really interesting.
Okay, so we've got these massive clouds of hydrogen getting denser, hotter. Sounds kind of like the inside of a star already.
It's getting there. Remember all those hydrogen atoms we talked about? Well, they're getting squeezed together tighter and tighter.
With all that squeezing, it's got to have some kind of effect, right?
Exactly. All that squeezing creates a ton of pressure, and the temperature at the center of these clumps skyrockets, eventually reaching a mind-blowing 15 million degrees Celsius.
15 million degrees. Okay, yeah, things are definitely heating up, and that's when things get really, really bright, right?
You got it. That incredible heat and pressure. That's the recipe for nuclear fusion. It's like someone just flipped a switch and boom, those hydrogen atoms start fusing together, releasing an incredible amount of energy. Our baby star is officially a star.
Talk about fireworks. So we've got our star blazing away, But what about all that other stuff? There was way more gas and dust in that cloud than just what went into making the star, right?
You're right. There's still a bunch of leftover gas and dust swirling around our newborn star, but this new star, it's got a bit of a temper tantrum going on.
A temper tantrum? What do you mean?
Well, this ignition, this moment when fusion kicks in, it's not exactly a gentle process. It sends out shock waves, blasts of energy that push away any leftover material that hasn't already fallen into the star. Think of it like a cosmic wind just sweeping through the system.
Okay, so we got our star, our cosmic wind, and this disk of leftover stuff. What happens to all the leftover stuff? Is that where planets come in?
Exactly. Yeah. But it's not like, poof, planets. It takes time and a whole lot of bumping around. We're talking about dust grains, ice crystals, gas molecules. They're all still swirling around the star in this disk, right? And as they orbit, they collide.
And I'm guessing it's a bit crowded out there, so those collisions happen a lot?
Oh, for sure. It's like a cosmic demolition derby. But instead of cars crashing, you have these tiny particles smashing into each other.
So after billions of years, you end up with a solar system, right?
Right. But, not all solar systems are created equal, and it turns out that where a planet forms in that disk, that really determines what kind of planet it's going to be.
You mean like how close it is to the star?
Exactly. Think about it, close to the star. It's incredibly hot, right? So only the densest materials can handle that heat, those rocky particles. They can take the heat. So they collide, they stick together, and they slowly grow larger. That's how you get the rocky terrestrial planets, Mercury, Venus, Earth, Mars. They're the survivors of that inner solar system where it's a real scorcher.
Makes sense. But then what about the outer planets, the gas giants? They're nothing like Earth.
And that's because way out there, past a certain point we call the frost line, it's a totally different story. It's so cold out there that stuff that would normally be a gas, like water, methane, ammonia, it freezes solid.
So instead of little grains of rock, you've got tiny ice crystals.
Exactly. And here's the thing, those ices, they're way more abundant than the rock and metal that make up the inner planets. So in the outer solar system, you have these giant planets forming around a core of ice and rock. But then their gravity pulls in all that surrounding hydrogen and helium gas, the most common stuff in the universe, and they balloon up into these gas giants we all know and love.
So Jupiter, Saturn, Uranus, Neptune, they all started with a core of rock and ice, but then they just kept on eating up all that surrounding gas, turning into these massive swirling worlds.
Exactly. And it's amazing to think that just a slight difference in temperature being inside or outside that frost line can make such a huge difference in what kind of planet you end up with.
It's like two totally different recipes with almost the same ingredients. It really makes you wonder just how many different kinds of planets are out there just in our galaxy alone. But okay, so now we've gone from this cloud of gas and dust to a fully formed solar system with a star at the center, rocky planets close by, and gas giants out in the chilly suburbs. And to think, it all started with a bunch of atoms bumping around in the dark. It's wild to think about, Like all this, our entire solar system, it all came from this giant cloud of gas and dust, and it took millions and billions of years for all to come together. And it makes you wonder, what's next, right? What's the grand finale for all this?
Well, the universe isn't done yet, not by a long shot. And one of the biggest clues about where it's going is that it's still expanding, even after all this time.
Right, we hear that all the time, the universe is expanding, but what does that actually mean? What is it expanding into?
That's the thing. It's not expanding asterisk into asterisk anything, at least not that we know of. It's that the fabric of space itself is stretching.
Oh, wait, hold on. So it's not that galaxies are, flying away from each other through space?
They are moving apart, but it's more than that. Imagine, little dots drawn on a balloon. Now, as you blow up the balloon, those dots spread apart, right? But the dots themselves aren't moving. It's the balloon itself that's getting bigger.
Okay, yeah, I see what you mean. So the universe is like that balloon. It's the space itself that's expanding.
Exactly, which is a pretty mind-blowing concept when you really think about it. And it makes the question of what's next for the universe even more wild.
So what asterisk is asterisk next? I mean, does it just keep expanding forever?
That's one possibility. It might just keep stretching, getting bigger and bigger, colder and colder, with galaxies getting further and further apart.
Sounds kind of lonely, to be honest.
It does, doesn't it? Like the slow fade into darkness. But there are other possibilities, too. Remember those mysterious forces? Dark matter and dark energy.
Yeah, the stuff that sounds like it came straight out of a sci-fi movie.
Exactly. Well, depending on how much of those things there actually are, they could change the fate of the universe completely. Imagine if there's enough gravity out there from all that dark matter, it could be enough to, counter that expansion.
You mean like put the brakes on the expansion?
More than that, it could even make the universe start to contract again.
Seriously? So everything would just start moving back together?
Exactly.
Yeah.
And eventually, it could all collapse back down into a single point, just like it started, a sort of Big Bang in reverse. We call it the Big Crunch.
Wow. So either we're headed for this big freeze where everything just keeps spreading out forever, or a big crunch where everything gets smushed back together. Talk about high stakes.
Right. And the crazy thing is, we still don't know for sure which way it's going to go. But that's what makes cosmology so fascinating. It's this giant puzzle, and every new discovery is another piece.
Well, I gotta say, I've learned a lot today. We've covered a lot of ground, from the very first moments of the universe, to the formation of stars and galaxies, to our own little corner of the cosmos here in the solar system. And we even talked about the ultimate fate of the universe, whether it's a big freeze or a big crunch.
It's a pretty wild ride when you think about it, this whole journey from the Big Bang to today.
It really is. And the craziest part, it's still going on. The universe is constantly evolving, changing, and it makes you realize that we're just a tiny part of something much bigger than ourselves.
We really are just a small part of this incredible cosmic story, a story that's still being written.
And that's what I hope our listeners take away from this deep dive. That next time they look up at the night sky, they remember that they're not just seeing a bunch of twinkling lights, they're seeing a snapshot of this constantly unfolding story of the universe.
A story that started billions of years ago with the Big Bang, and a story that we're all a part of.
Well said. And on that note, I think it's time for us to sign off. Thanks for joining us on this journey through the cosmos. We'll see you next time for another deep dive.